One last thing we can ask when dealing with our galaxy is, so what's our position within the galaxy? The first attempt to try and figure out where we're located in the galaxy decided to use the distances to the most luminous stars. The idea is that our galaxy is disk-shaped, and as we figure out the distances to the stars, that's going to trace out the edges of the galaxy, and if we know where the edges are, then we can figure out our position inside. So, for example, if you think about a disk, and if you're right in the center of the circle, then the edge to the circle is always the same distance away. As you move out away from the edge, then one side is going to get closer, and the other side is going to get farther away. So as we trace out the edges of the galaxy, then we can figure out our position inside. Well, as they went through and they figured out these distances to all of these most luminous stars we could see, they found that they were all roughly the same distance, meaning that we were the center of our galaxy. And we're most definitely not the center of the galaxy, so something was terribly wrong. The problem with this first attempt is that it didn't take into account interstellar extinction. Interstellar extinction is that idea that the interstellar medium blocks visible light. So what this means is that we're in the center of what we can see. As we're looking around us, specifically through the disk of the galaxy, it's kind of like being in a fog. If you've ever been in a fog before, as you look around, you can see maybe 10, 20 feet if it's a thick fog. And no matter what direction, you can see that same 10 or 20 feet around you. That does not mean that you're at the center of the fog. It means you're in the center of what you can see. And that's exactly what was happening in this case. If we try to look through the disk of the galaxy, we're trying to look through the interstellar medium, which is like looking through a fog. So we can only see the distances around us that allows the light through. If we want to actually figure out where we are, or to figure out the true scale and size of things, we're going to have to look out of the fog. In other words, we cannot look through the disk of the galaxy. Now remember, all of the interstellar medium is located through the disk. So if we look out into the halo and figure out the distances to stuff out in the halo, then we'll be able to figure out the size of the galaxy and our position inside. Fortunately for us, we've got globular clusters out in the halo. So if we can figure out the distance to the globular clusters, then we'll be able to figure out our position within the galaxy. The way that we've been able to determine the distance to globular clusters is by looking for a type of star called an RR Lyrae variable star. Here is our fourth lecture quiz question. Why do stars twinkle? A. The star is changing in brightness. The star itself is changing. B. The turbulence in the Earth's atmosphere refracts the light. Or C. As the interstellar medium moves, it blocks more or less light. Go ahead and think about it, and we'll discuss in just a bit. So why do stars twinkle at night? The correct answer is B. It's all because of the Earth's atmosphere. Okay, so it is B. So although stars twinkle at night because of the refraction of the Earth's atmosphere moving around, there are actually certain types of stars that they themselves are changing luminosity. As we look at the HR diagram, most of these stars are located between these two dashed lines in this region referred to as the instability strip. These stars frequently change in luminosity. At the top of the instability strip up here, we have a type of star called a Cepheid variable. This is named after Delta Cephei in the constellation Cephus, which was the first star ever discovered that did this. What's interesting about these Cepheid variables, other than they themselves are changing luminosity, is the reason why. As we look at their Doppler shift, we see that they're changing luminosity because they're actually growing and shrinking in time. These stars pulsate. So as they grow larger, they become more luminous, and as they shrink back down, they become less luminous. Here is our fifth lecture quiz question. What do we need to determine a star's distance? A, color and mass, B, mass and luminosity, C, luminosity and brightness, or D, mass and spectral type? Go ahead and think about it, and we'll discuss in just a bit. So what do we need to determine distance? It is C, luminosity and brightness. So luminosity is how much energy the star is actually giving off. Brightness is how much of that light we actually see. So if we know how much it gives off and then how much we receive of that light, we can figure out how far away that star is. Now this is going to be a recurring idea. Make sure you get it down, that to figure out distances, we need luminosity and brightness. Well, Cepheid variables are interesting because they pulsate, they grow and shrink in time, but they're also very, very useful. As we have studied them, we have found that there's a relationship between their pulsation rate, their pulsation period, how long it takes for them to grow and shrink and grow again, and their luminosity. Which means, as we study how they pulsate, we can then determine luminosity, and once we know luminosity, we can then figure out distance. Well, related to the Cepheid variables, those are the ones up here on the top of the instability strip. Down towards the bottom, we have the RR Lyrae variables. These ones are kind of like the little brother to the Cepheid. The Cepheid's the big, bright one. The RR Lyrae still do the same thing, but they're not as large or luminous. Because of the age of globular clusters, they actually contain RR Lyrae variables and not Cepheid variables. So we can study the RR Lyrae, which have their own period luminosity relation, which will then allow us to determine the distances to the globular clusters. Now, one quick side note, something that's kind of interesting about these RR Lyrae, as they expand, they can actually expand fast enough that their outer layers reach escape velocity, which means every time they expand, they kind of puff a little bit of stuff, which is kind of fun. So, based off of the distances to the RR Lyrae variables in these globular clusters, we've been able to determine that our sun is about 8 kiloparsecs, that's 1,000 parsecs, from the center of the galaxy. That puts us somewhere around 24,000 to 25,000 light years from the very center of the galaxy, which means we are not the center of everything yet again. We've also been able to determine the size of our galaxy. Altogether, our galaxy from edge to edge is around 50 kiloparsecs, okay? So around 100,000 light years or so across.